Hey everyone, the purpose of this video is to give you an example of by far the hardest calorimetry problem you could ever expect to get. And I highly doubt it that you would ever be expected to demonstrate something this complex. However, I did want to go over it with you, and I'm going to point out the level I think you might be asked on an AP exam and what you should be aware of ultimately as you move on to college, and the level of understanding of and awareness of what you might be expected to do, perhaps in college. But for this year's AP, I would highly doubt something this intricate would ever be asked. That said, let's take a look at this problem. You want to determine the delta H for this reaction. And remember that the delta H can be achieved in any number of ways. So there's lots of theoretical ways to do it, but in this particular example, it says we're going to do it through the process of calorimetry. And to do so, you must first determine the heat capacity of a calorimeter using the following reaction, whose delta H is known. So when you mix sodium hydroxide and hydrochloric acid, both of which are aqueous solutions, you produce sodium chloride and additional liquid water. Notice that delta H is negative, so what that's telling us is this is an exothermic reaction and that heat is a product. Now, as you learned in the reading, a calorimeter itself usually absorbs a small amount of the heat energy. So not all of the heat energy lost in a chemical reaction or released in a chemical reaction necessarily goes into the solution. The cup itself, while it's made of styrofoam, will absorb some heat. So the way to think about this, and the way I like to think about all calorimetry problems, is as such. Really, if you start to think of it in this term, in this framework, let's just say, calorimetry is about measuring the heat lost typically from some chemical reaction and gained by something else. And the way this is typically represented is minus Q reaction equals, so if a chemical reaction, I'm just going to sort of frame this in an exothermic way, although it could be endothermic. Minus Q reaction, so let's say it's exothermic and heat is produced in your chemical reaction. So the reaction itself produces heat, right, from the process of the fact that some chemical bonds are broken, right, the reactants, and some chemical bonds are made, the products. And if it is exothermic, the product is lower energy, more stable, and so therefore heat is released. That said, what's gaining the actual heat is, whoops, that's not a G, it's a Q. So what's gaining the heat is the solution itself. So the reaction, the chemicals, the molecules in the reaction from the making and breaking of bonds are on the left-hand side, right? Now on the right-hand side, if heat's being produced, it's being absorbed by the solution itself, right, the water and its contents, and I'm going to call this QCal. But what QCal really stands for is the calorimeter cup itself. So the calorimeter cup is made of styrofoam, doesn't absorb a lot of heat, but it will absorb quite a bit. Now, in almost every single FRQ I've ever seen on the AP exam, this is either essentially zero or not even mentioned. So if you read a problem and there is no mention of a calorimeter, then you just assume that the calorimeter absorbs nothing. So if it's this type of reaction run inside of a coffee cup calorimeter and nothing is mentioned at the calorimeter, you're assuming this is zero. But like I said, this is a hard problem, a complex problem, and so what we are going to do is we are going to determine, in fact, what the calorimeter does absorb. The way you typically do this, if we were doing this in a lab, you have 1 cup, you have, let's say, 50 mils of, let's say, cool water, water temperature water. Let's call it 20 degrees Celsius, okay? And then what happens is you warm the same volume of water, right? You warm 50 mils of water in a beaker, and let's say you make it 40 degrees Celsius, right? You dump it in, so you measure right before you dump it in, right? This other water, and again, another 50 mils, and you know that it's 40 degrees because you measured it right before you dumped it in. Now, if this coffee cup calorimeter were perfect, right, it would absorb no heat. But what you notice is when you mix exact volumes together of water, you would expect it, right? So if you mixed 40 degrees and 20 degrees, if you mix the same volumes, like we did, 50 each for 100 total, you would expect the temperature, right, to be smack dab in the middle, the average temperature to be 30. However, it's always a little bit lower because the cup itself absorbs a little bit of that heat energy. So the difference between what you expect it to be, 30, and what it turns out to be, let's say 29.6, that 0.4 degrees difference is due to heat absorbed into the cup itself. So this question asks us to determine Q calorimeter a slightly different way. Because it's giving us the heat released in a chemical reaction, and then we're going to look for what number we do get versus the theoretical answer we should get. And what we're going to assume then, of course, is that the difference between theoretical, what should be, and experimental, what is going to be due to heat absorbed by the cup. That said, calculate the heat capacity of the calorimeter from these data. Amounts used: 50 mils of 2 molar HCl and 50 mils of 2 molar NaOH. So we have equal volumes and we have equimolar. Initial T of both solutions is 16.9. That's good, so that we don't have to worry about some initial temperature being different. Because if they started at slightly different temperatures, then it complicates the process more. The maximum temperature reached is 30.4 degrees Celsius. The density of the resulting solution is 1.04 grams per mil, and the lowercase c of 1 molar HCl is 3.93 joules per gram degree Kelvin. So now what we're going to do is we are going to determine what the delta H of our calorimeter is from this process. Okay, so this right here is what we are solving for. So you could do this in one giant step, and by doing it in one giant step, you can sort of see how we're going to preserve what's happening. So I'm going to leave minus Q reaction on the left-hand side here. Now, what I'm going to do is take the number that we were given at the beginning, okay? 57.32 kilojoules. Now, this is delta H, and so technically, it's really kilojoules per mole. I hand wrote this in earlier because it got cut off. So delta H is always kilojoules per mole because it's the sort of normalized number that we can use that's universal. So 57.32 kilojoules per mole. Well, I guess one thing we need to know is how many moles of reactants are we using here? And in this particular case, there is no limiting reagent because what we noted is that 50 mils of 2 molar HCl and 50 mils of 2 molar NaOH are going to have equal moles of H plus and NaOH minus, equal moles here and here. So there is no limiting reagent. They run out at the exact same time because it's a one-to-one reaction. So what we just need to do is figure out and normalize this to however many moles we used, right? So this could get a little messy in one equation, so here's what I think we're going to do. We're just going to solve first for Q reaction. So, Q reaction is a little different than how we're going to conceive of it in the calorimeter. What we have is that number, right? So we have 57.32 kilojoules per mole. So that is minus 57.32 kilojoules, okay, per mole of reactant. Now, let's convert our kilojoules to joules, okay? 1,000 joules in a kilojoule. Next, we really wanted to know however many moles we're using, right? So if we had we had 2 molar solution and we had 50 mils of it, right? So 2.00 moles per liter times 0.0500 liters, and with this we figure out the number of moles of both, HCl and NaOH. Now, because they run out at the same time, there's no limiting reagent. If there was a limiting reagent, that's the moles we'd be using right now. But either one is fine because they run out at the same time. So, what we find by setting it up like this, Q reaction is equal to negative 5732 joules. So in the end, what's happening is this reaction should be, in theory, releasing 5732 joules, and does release that amount of energy. Now, how much did the solution itself absorb? That quantity is not a theoretical number, right? But instead, what we're going to measure. Now, what I'd also like to point out is that I sort of dropped this negative right here, and it's going to come back here in a moment when we put it into this equation. But if I'm just solving for Q reaction, I'm going to leave it negative for now. Q solution is the mass of our solution times C, the specific heat capacity of our solution, times delta T, the temperature change, final minus initial of our solution. Now, I do recall from the problem that we are given a density of solution here, right? So 104 grams per milliliter. And when I run this reaction, my total solution volume is actually 100 mils because I'm adding 50 and 50 together, right? So 100 mils times my density, right? 1.04, right? 1.04 grams per milliliter will tell me the mass, right? Check, of my solution. And the problem also gives me my specific heat capacity. When I look up in the problem, again, it was 3.93 joules per gram K. Now, again, remember what this means is it takes 3.93 joules of energy to raise 1 gram of this solution 1 degree Kelvin or Celsius. And the reason is because Kelvin and Celsius, while they are shifted scales, 1 degree is equivalent for both, the 1 degree change. So basically, to go from 20 to 30 degrees Celsius, if on the Kelvin scale, it is also a jump of 10 degrees. And because we are talking about deltas here, right, delta T, we can just use those two temperature scales interchangeably. So now our mass will cancel, right? The grams cancel. Now, in order for this math to work out, I need to multiply by my delta T, my last change of change of temperature in this solution. And it's always final minus initial. So 30.14 minus 16.9. And here's my degrees Celsius, or K. And when I multiply through by this, I am left with joules. And when I do this, I get an answer of 5518 joules. Now, there is a difference between my reaction and my solution. And that difference is the amount of heat absorbed by my calorimeter. So here's where I plug and go back to my original equation of minus Q reaction equals Q solution plus Q cal. Minus heat lost equals heat gained. And the reaction's losing and the solution in the calorimeter cup are gaining. So let's replug this into our equation. So therefore, this negative gets accounted for again. Negative 5732 joules. And you can't forget to put that negative Q reaction in. Because if you don't, this whole answer goes to pot, or this whole equation. 5518 joules. And then Q calorimeter is what we're solving for right now. This is our Q solution, this was our Q reaction. So now, when I solve for this, I get a number of 214 joules as Q cal. Now that's the amount of heat absorbed by my cup. However, what's really important to notice, and this is something we would have done in the lab and explained then, is that's the amount of heat over this particular temperature range. Notice that we had a temperature change of 30.4 minus 16.9, right? So over a change of delta T of this, that is how much heat is absorbed. So what we really need to do in order to go from Q cal to capital C cal, what that means is we're going to go from the heat absorbed by the calorimeter in this particular case to how much heat will my calorimeter absorb over a given temperature range or per degree. I need to do one conversion, and that conversion is I need to divide my joules by the delta T. So I'm going to take my 214 joules and I'm going to go back to my delta T because the cup, right, I think that was 30.4, not 0.14. 30.4 minus 16.9, and that's either K or C, and I get 15.9 joules per degree Celsius or Kelvin. So this is what's known as the heat capacity of my cup, capital C. And I know this seems a little confusing, and what's the difference between big C and lower C? Lower C, sometimes lower S, is called the specific heat capacity, or just sometimes called the specific heat, and that is for a substance. So essentially, what that means is, I'll take water for an example, 4.184 joules per gram degree Celsius. Capital C is called the heat capacity, not specific heat capacity, just the heat capacity. And this is typically for an object like a calorimeter. And unlike a substance of no defined amount, a calorimeter has some heat capacity, and the units are joules per degree Celsius. Notice the difference between these two units. The one on top has grams, the one on bottom doesn't. And the reason is because it is for an object. It is for that specific cup. It is not for styrofoam. So when I see 15.9 joules per degree Celsius, that means for every degree Celsius change that this cup sort of experiences, it's going to absorb 15.9 joules of heat. So the grams is worked into the 15.9 because it is an object. Because it is a whole cup, not a substance like styrofoam or water. So, just to go back and reiterate what we've done, we have now solved for the heat capacity of our cup, our calorimeter itself. That said, we now are going to use this value moving forward, because that was just part A of this really difficult experiment. So what I'm trying to do here is essentially condense the experience of a lab, a whole calorimetry lab that we would have done over a couple days, into a theoretical problem. I highly doubt, like I said, the AP exam would have something this involved. In fact, I'd bet my life they wouldn't. However, I'm going to go through this process just so that you understand, where this is all coming from. Now that you know what the cup absorbs, you can use this data to solve, ultimately, the original question that was being asked, right? To experimentally determine the delta H for this reaction with solid zinc, right? Solid zinc reacting with hydrochloric acid. So now let's turn to part B. Use the result from part A in the following data to determine delta H reaction for the reaction between zinc and hydrochloric acid. So, 100 mils of 1 molar HCl and 1.3078 grams of zinc. We have an initial temperature of 16.8. We have the maximum temperature recorded. We have a density of solution. And we have the specific heat capacity of the solution. All right, so now we're determining delta H reaction. So, if I were taking the AP, right, part B. So, minus Q reaction equals Q solution plus Q calorimeter. And like I said, most problems on the AP exam would eliminate the calorimeter part that we just did. And you'd either be given that value or it would just simply be ignored. So what we're doing now, if you can see the context of this, is we're determining essentially what our Q reaction is. And we're going to do that by incorporating the calorimeter data from above as well as using Q solution data. So now, minus Q reaction is our unknown. And in this reaction, what we're doing is we're going to break down Q solution and Q cal. So Q solution is the mass of the solution times the specific heat of the solution times the delta T experienced by the solution, and we're going to do Q cal, which, remember, capital C takes into the grams into account, so there's no mass to multiply. So it is capital C from above times our delta T. What this results in is joules here and joules here that we're going to add together. So, how do we determine the mass of our solution? Well, we do have the density of our zinc solution, right? We have 1.015 grams per mil, okay? Times 100 mils. And that's for the HCl part. But we also added a solid portion of zinc, right? 1.3078. So this constitutes the mass of our solution, okay? The HCl mass on the left added to the mass of zinc solid. That will, of course, react away, but nonetheless, the weight is still there, right? So now we have the mass. Now we also have, from our example above, the specific heat of our solution, which is 3.95 joules per gram degree Celsius or K. And we have a delta T of 24.1 was our final in our data, and our initial was 16.8. So 24.1 minus 16.8. Okay? So what we've just done, okay, is this portion of the calculation. And rather than moving to the right, I'm now going to do this portion of the calculation here. We're going to take our heat capacity that we solved for above, 15.9 joules degrees Celsius, and we're going to multiply by that same temperature range, 24.1 minus 16.8. And when all is said and done, we're going to get a value for joules here and a value for joules here. And then we're going to add those up. And when I add those up, I get the number 3080. And if you'll notice from these numbers, because the delta T is always bigger minus smaller for exothermic reactions, this number actually turns out positive, right? But don't forget what we're using. We apply our negative number all the way from the top above, and so this now gets a negative, is my negative Q reaction, okay? So my Q reaction is now negative 3080 joules. Now, of course, I'm very close, but I'm not quite finished yet. In order to do this fully and convert this to delta H, okay, I need to figure out how many moles of HCl and zinc I used, and then figure out which one is limiting. And so when I figure out which one is limiting, if there is a limiting, then that's the number of moles I used, because that's how much actual reactants were used total. And when I look back at my equation, it was 2 HCl plus solid zinc, right, giving me H2 gas and ZnCl2 aqueous. So a little bit of quick math to begin with. If I take the amount of solid zinc, which is 1.3078 grams, and I incorporate its molar mass, I end up with 0.0200 moles of this. And then when I take the molarity of the HCl originally, which I believe is 1 molar, times, 100 mils or 0.1 liters, I get 0.100 moles of HCl. So, what's clearly the limiting reagent, right, is going to be the zinc. And so, therefore, the zinc runs out first because I definitely have 0.04 moles, right, of HCl, which because I need double of that, and then the zinc is gone. So I've reacted 0.02 moles of zinc and double that of HCl. But we always normalize to the 1 mole, and because the zinc has the 1 in front of it, we're just going to take our negative 3080 joules and divide it by 0.0200 moles, and we will get a number of negative equals negative 154. I'm going to convert to kilojoules because it's so big. Kilojoules per mole is our equals the delta H reaction, right? And the moles, right, were incorporated to take our joules, right, which is just happens to be for the amounts for this reaction, our Q reaction. And when I divide by the moles used, I convert it to something much more usable, right, which is the delta H. And for the final part of this problem, let's just take a quick look back at part C. And part C asks us, given the values below, what is the error in your experiment? With this, I'm not going to go through this. We're already half hour into this video. But delta H reaction, right, we've done these before, equals the summation of delta H formation of products minus the summation of delta H formation of the reactants. And then they give us delta H formation values for ZnCl2 and HCl. So the products minus the reactants, we look back at the chemical reaction, right? And one of the things I want to note is that right, in our for our reaction up here, right, because H2 is a gas in its elemental form, the delta H formation of that would be 0, and then the delta H of solid zinc, right, zinc in its elemental form would be 0. So you could easily just do products minus reactants for HCl and ZnCl2, right, ZnCl2 minus 2 times the value for HCl, and that number should come out to something very close to what we got here, right at the end. And then right at the end, allowing you to figure, right, it should come out close to something near negative 154. I think I did it myself a little earlier, and it came out to negative 151.8 kilojoules per mole. So that's the answer to part C. If you want to do that on your own, that's the final answer. So like I said before, this is a very, involved, complex calorimetry problem. I just wanted to basically teach to the sky high here, the 5++. I'm sure nothing would ever be this detailed. When you're looking at these on the AP exam, I think almost all of the time you just may be asked a question, well, how much heat was absorbed or released? And, you're going to be just basically applying one of these Q equations of M times C times delta T in an isolated context, nothing nearly as complex as what we just did. Okay? However, like I said, I wanted to show you and shoot for the stars here. The problems I've assigned are much simpler, and I can even make a separate video introducing those if you feel that you would struggle to answer those. But for now, going to say goodbye and hope you found this useful.